Dear students, in today's video, we are going to discuss important application of Gauss law. We are going to calculate electric field intensity due to thin infinite plane sheet of charge. In the figure, we can see that we have a thin sheet which is positively charged and we want to calculate the electric field at point P. This point P is located at a distance r from sheet. The question will appear in the exam that apply Gauss law to calculate the electric field due to an infinite plane sheet of charge. So, the charge on the sheet is positive and it is uniformly spread throughout the sheet. So, we define sigma as uniform surface charge density such that sigma is the ratio of Q by A. A is the area of the sheet and Q is the total charge present on the sheet. We want to calculate the electric field at point P and R is the perpendicular distance of point P from the sheet. Then we compare that R is very small as compared the size of the sheet. So, the sheet can be considered as infinite as compared to the R. It is important to know what is the direction of electric field produced due to this positive charge. We know that the positive charge has electric field lines directed away from it. As the sheet is positively charged, the direction of electric field is outward and it is perpendicular to the sheet. If this is sheet, then the direction of electric field is perpendicular and it is equal on both sides of the sheet. To calculate the electric field, we need to apply the Gauss law, right? And for Gauss law, our requirement is to choose a Gaussian surface. At point P, we consider a cylinder which is a Gaussian surface. This cylinder has this circle at the center and the point P has distance r from it. Similarly, on the another side, the distance will be r. So, the total length of the cylinder is 2r. So, the chosen cylindrical Gaussian surface has cross-sectional area A. This particular area is A, this area is A and this area is A. And the length of the cylinder is 2r. Then we calculate Q in. The total charge inside the cylinder will be given as sigma into A. This A is the cross-sectional area of this circle. Then this Gaussian surface can be divided into three regions, region 1, region 2 and region 3. The region 1 is this circular region 2 is the another end circle and the region 3 is the curved area of the cylinder. We apply Gauss law. Gauss law states that the electric flux is equal to surface integral of electric field and the area vector and it is equal to Q in divided by epsilon naught. Q in is the total amount of charge present inside the Gaussian surface. So Gaussian surface is divided into three regions. First region, second region and the third region. The region 1 has area element ds1. So this is the area element of region 1. It is written as ds1 into n cap. N cap is the unit vector perpendicular to the ds1 and we know that the electric field from plane sheet of charge is also perpendicular to the sheet. So both n cap and E vector has same direction. So ds1 and E are parallel to each other. So the dot product A vector dot B vector can be written as AB cos of theta, right? And in our situation, as they are parallel, theta is equal to 0 degree which is equal to 1. So it is E ds1 cos of theta cos 0 1. So it comes out to be E ds1 only. Similarly, for the region 2, it will be E ds2. Then we substitute the things for E ds3. In E ds3, this is the area element, right? The unit vector is perpendicular and electric field is in this direction. So the angle between them is 90 degree. So when you make the substitutions, cos 90 degree is equal to 0. So it comes out to be 0. Then we calculate the phi. It will be coming from region 1 and 2 only. So E is constant. It comes out of the integration. The integration is left over the ds1 only. When you take the integration over ds1, it will give you the value a. So it comes out to be 2ea, and phi is equal to 2ea. The another expression for phi is q in divided by epsilon naught, as from the Gauss law. So we make the substitutions, we get this expression, and by cancelling a on both sides, the electric field comes out to be sigma by 2 epsilon naught. It can be clearly seen from the expression that electric field is independent of the distance r from the plane sheet. So if you plot a graph of electric field versus the distance r, then the electric field is not going to change with the distance. It has fixed value whether the observation point is moving away from the sheet. And the value is equal to sigma divided by 2 epsilon naught, where sigma is the surface charge density and epsilon naught is a constant. Sigma can have two possible values. One is sigma can be greater than 0, another is sigma can be less than 0. If the sheet is positively charged, the sigma is greater than 0. So the field is directed away from it, as the electric field lines from the positive charge moves away from it. And if sigma is less than 0, means sheet is negatively charged and the field will be directed towards the sheet, because we know that for the negative field, the electric field lines are toward the negative charge. This is all about the electric field produced due to thin infinite plane sheet of charge. Kindly like, share and subscribe the channel. Thank you.